Hi guys, welcome back to the channel. In this lecture, we are going to discuss about the shape vector, right? In the last lecture, we have discussed how to calculate what is the formula for shape vector and what is the significance of the shape vector. Okay, as per our discussion in the last lecture, the shape vectors comes out to be the ratio of the plastic section modulus to elastic section modulus, right? And this it tells us about the shape vector, basically the unreserved strength of a cross section, right? So in this lecture we will be going to discuss how to calculate shape vector for different cross section. Okay, so let us suppose if you have a simply supported beam, right, and this beam can be of any cross section, right? It may be circular, it may be rectangular, it may be I-shape, it may be diamond shape. Okay, so what we are doing is that we are calculating the shape vector for different cross section of the beam, right? So now let us suppose we are having one cross section, okay, which is circular, this is circular section, and the radius is basically r, small r, right? The plastic section modulus is defined by this formula: Zp equals to area divided by 2 y1 bar plus y2 bar. Okay, this we have discussed in the last lecture. Okay, what is this y1 bar and y2 bar? Okay, so when we are calculating the plastic section modulus, this section has yielded. Okay, each fiber has yielded means each fiber reach to the sigma y value, right? So when each fiber has yielded in this cross section, the neutral axis will be termed as plastic neutral axis. Okay, this is basically plastic neutral axis. Okay, and in the section is symmetrical about both the axes. This is, let us suppose this is x axis and this is y axis. Okay, so when the section is symmetrical about both the axes, our neutral axis will coincide with the plastic neutral axis, and this axis will also be our neutral axis. We will use this axis when we will be calculating the plastic section modulus or elastic section modulus, right? This plastic neutral axis divide this area into two equal parts, right? One this area and one this area, right? Now the y1 bar is basically the centroid of this area. Okay, this is y1 bar and this is basically y2 bar. Okay, so now if you want to calculate the plastic section modulus, area is basically area of cross section, which will be equals to pi r square. Okay, y1 bar will be equals to the, if you have this type of cross section, this is so the centroid will act at a distance of 4r over 3 pi. Okay, this formula you can see in strength of material books, right? So the centroid will be 4r over 3 pi. Okay, and this is symmetrical cross section, so y2 will be 4r over 3 pi, right? So if you put this formula, if you put these values into this formula, it comes out to be, this is 4r over 3 pi plus 4r over 3 pi, right? So pi will cancel out, will cancel each other. So the value comes out to be, this will be 8 over 6 r cube, right? So this will be 4 by 3 r cube. Okay, 4 by 3 r cube. This is the value plastic section. This is the value of the plastic section modulus. Okay, 4r over 3 cube, right? Now we need to calculate what will be the value of elastic section modulus. Okay, and elastic section modulus, we need to have neutral axis. Okay, so this cross section is symmetrical about both the axes, so this neutral axis will coinciding with this plastic neutral axis. Okay, so neutral axis will also pass through this center. Okay, so now for this ZE, we are having this formula I over Y max. Okay, why Y max? Because Y at extreme fiber will yield first. Okay, so these two fibers will be yielding first. Okay, there will be a compression yielding, there will be tension yielding, depends upon the direction of the load also. Okay, so I is basically the second moment of area, the second moment of area of this cross section. Okay, this cross section, right? And basically I will be taking this moment of inertia basically, or second moment of area, I will be denoting by Ixx. Okay, Ixx, right? Okay, so when we calculate the moment of the first moment of area for this figure, this second moment of area about this x-axis, so it will be I'm assuming that load is acting like this. Okay, it will be pi r4 over 4, right? This is the value of second moment of area about x-axis, right? So if you put this, and y max is basically the radius. Okay, this extreme fiber is at a distance r from this neutral axis, right? So this value will be pi r4 over 4 into r, right? So this will cancel. So ZE value will be pi r cube over 4. Okay, so if you put this value into this shape factor formula, so the value will be, shape factor will be pi r cube into 4. R cube cancel, so 16 divided over 3 pi. 16 divided by 3.14 divided by 3. This is 16 divided by 4 into 3. So the value comes out to be the value comes out to be 1.698. Okay, so the value of the shape factors comes out to be 1.698, right? Which means, what is the significance of this shape factor value? It means that this particular section can sustain 69% more moment than the yield moment, right? So this is the significance of the shape factor. Okay, so in case of this what you can say that in case of the circular cross section, the value of this shape factor is basically, shape factor for circular cross section comes out to be 1.698, right? So this is the, what you can say that the shape factor for the circular cross section. Now we will be calculating the shape factor for the thin hollow circular cross section. Okay, so thin hollow circular section will look like this. Okay, so let us suppose this is the R, right, and the thickness is basically T. Okay, as this is a thin circular cross section, this T T is less than, very less than this R value. Okay, that's why this is thin circular section, okay. So we need to calculate the shape factor for this cross section. Okay, shape factor will be the ratio of plastic section modulus, which is ZP, to elastic section modulus, which is ZE. Okay, and again it basically tells you about the unreserved strength of a cross section. Okay, so now let us solve this problem. So ZP is nothing but, ZP will be A by 2 into Y1 bar plus Y2 bar. Okay, so now we will be calculating this plastic section modulus. Okay, and later we'll calculate the elastic section modulus. Okay, and again you can see that this is symmetrical about both the axes. So the plastic axis and neutral, so the elastic axis and neutral plastic axis both will coincide. Okay, and it will pass through this point, this center. Okay, and this plastic neutral axis will basically divide this cross section area into two equal parts, right? We'll be dividing this cross section area into two equal parts, right? And what is the cross section? Cross section is basically this cross section. Okay, because this cross section will only take the bending stresses, right? And this is hollow from inside. So area we need to calculate, as this is the thin circular section, I can write the circumference, the average circumference will be 2 pi r. Okay, and if I multiply it by thickness, then it is the area of this cross section, right? So now this thing is done. So I will put this value. And what is the value of this Y1 bar? Okay, if you have this thin circular section, this is not circular basically. Okay, so its centroid will lie at a distance of 2r over pi. Okay, again this formula you can see in the strength of material books, right? So Zp is basically equals to 2 pi r into T divided by 2 into Y bar will be 2r over pi. Again this is a symmetrical figure, so again the Y2 bar will also be equals to 2r over pi, right? Now if you calculate this value, this 2 will cancel out, this pi will cancel each other. So this value comes out to be 4r square T. Okay, and this is the value of the plastic section modulus. Okay, now we need to calculate what will be the value of elastic section modulus. Okay, so elastic neutral axis will be coinciding with the plastic neutral axis, already discussed. Okay, so okay, and I'm assuming that bending is taking place about this axis, right? So this is also our elastic neutral axis, right? So we need to calculate the moment of inertia, or you can say that second moment of area about this x axis. Okay, and how to do that? So for that I'm taking at a distance of r theta, at a distance theta, I'm taking an element which is, this element is basically r, small r d theta. Okay, and this thickness is basically T. So if you calculate Izz, it will be r d theta into T into r square. Okay, this is the first moment of area, the second moment of area of this element about zz axis. Okay, and we have this formula Izz equals to Iyy plus Ixx. Okay, so here this is symmetrical about both the axes, so I can write 2Ixx equals to 2Izz, right? So my Ixx will be Izz about 2. Okay, so I'm calculating the second moment of area about this axis, right? but we need to calculate the second moment of area about this axis. Okay, so I'll be using this relation. First I will be calculating the IZZ. Okay, this element, the second moment of area of this element about this axis. So it will be area of this element into this distance, which is basically r square, right? This relation I'm using, AR square. So A is basically this r d theta into t, area of this element, into r square will give me the second moment of area of this element about this axis, right? So if you integrate this thing, from 0 to 2 pi, so the value comes out to be, this is nothing but 2 r cube t, 2 pi, okay, 2 pi r cube t. Okay, so this is the IZZ, okay, and I axis will be half of it, so it will be pi r cube into t. This thing you can see in any strength of material books, okay, this how to derive this IZZ, right? So this is basically pi r cube t is our I axis. The bending is taking about this axis only, right? Let us suppose this is the direction of the load, okay. So the elastic section modulus will be ZE will be I XX over Y max, okay. So I axis is nothing but it is pi r cube into t over Y max is basically the extreme fiber, okay. So I'm taking that mean basically because t is very, very small, so it will be r. So this is nothing but pi r square into t. So this is the value of elastic section modulus, right? And shape factor is equals to Zp over Ze. So shape factor, if you put the value of this formula in this formula, so this is 4r square t over pi r square t. R square t will cancel out each other, and the value of this shape factor will be 3.14. It is 1.27. Okay. So this section, this circular cross section can sustain 20% more moment, 20% more moment than yield moment, which is basically My. Okay. So this is the significance of this, what you can say that shape factor. Okay, here the shape factor for hollow section, hollow thin circular section is 1.27, right? Now we will be calculating the shape factor for this, what you can say that for diamond cross section, okay, and we'll see what value will come for the shape factor, okay, and we'll come to some result after that. After analyzing these three structures, after analyzing these three cross section, we'll conclude some result from that, okay. Now let us calculate the shape factor for diamond cross section, for diamond shape cross section. Okay, so diamond shape will look like this. Okay, this is the total width, which is B, and this is H, and here also this is H. Okay, we need to calculate the shape factor for this diamond shape cross section. Okay, this is diamond shape cross section. Okay, so if you want to calculate the shape factor for diamond shape cross section, again we need to calculate the ratio of plastic section modulus to elastic section modulus. Okay, so again this cross section is symmetrical about both the axes, so plastic neutral axis will coincide with the symmetrical elastic neutral axis, and the plastic neutral axis will divide this cross section area into two equal areas, okay, and it will pass through this axis only, right? So this is our plastic neutral axis. Okay, so plastic section modulus we will be calculating by using this formula, a by 2 y1 bar plus y2 bar. Okay, so this is y1, this will be our y1 bar, and this will be our y2 bar, and these are two our equal. This is a by 2, this portion, and again this is a by 2 above this plastic neutral axis, and one area is below the plastic neutral axis. Okay, we'll put this value, we will put this all this value into this formula. So area will be it will be half into b into h into 2. Okay, because there are two cross section area, so this two, it will, area is equals to b into h, right? y1 bar will be equals to the centroid of this this cross section will lie at a distance 2 by 3h. Okay, right? So this is, if this is the cross section, so the centroid will lie at a distance of h by 3. This distance is h by 3, and again this distance will be h by 3. Okay, so this is basically h by 3. This is again h by 3, right? So if you put this value into this formula, Zp equals to area bh by 2 into y1 bar is h by 3, and this value is again h by 3. Okay, we are calculating the centroid from this plastic neutral axis. So its value will be bh square over 3, right? So this is Zp. Now we need to calculate what is the elastic section modulus. Okay, so if this is the cross section and this is our elastic neutral axis, so the elastic neutral axis will always pass through the centroid. Okay, when we are in elastic state, so this is our centroid, so it will pass through this line only, right? So again I need to have Zp, we'll need to have one moment of inertia, or you can second moment of area about this axis, and the y max. Okay, so I axis will be the second moment of area about this axis. Let us suppose this is b and this is h. It is bh cube over 12. Since there are two cross section, one this cross section and one this cross section, it is multiplied by 2. So it is bh cube by 6, right? So now, and Ze will be equals to bh cube by 6 into my y, divided by y max, because this extreme fiber will yield first. So y max will be, y max is basically it is h, so h will cancel, it is, this is bh square over 6, right? So again, if you put the Ze and Zp value into this formula, you will be getting bh cube, bh square over 3 into bh square over 6. So you are getting the shape factor value basically 2. Okay, okay, so which means that this section, this diamond cross section can sustain 100% more moment than yield moment. Okay, So this is the meaning of shape factor. The shape factor for diamond shape cross section is basically comes out to be 2. Okay. Now the important thing. So why this variation is basically coming, right? So if you see the shape factor for this circular cross section is basically this is 1.698. Okay, and shape factor for this hollow thin circular section is 1.27, and shape factor for this cross section is 1, 2. Okay, so why there is this variation? Basically, as you can see that when we are applying load on this cross, when we are applying load on the beam, when we are applying load on this beam, first let us suppose it is having this circular cross section. Okay, so when you are applying load on this beam, this circular cross section will bend. Okay, it will subject to some compression and tension, some bending stresses. It will subject to some bending stresses. Okay, outer fiber will yield first. Okay, these outer fiber will yield first. Okay, now if this outer fiber will yield first, okay, and you will know that for the bending, for the if the cross section is need to be designed for bending, it should have maximum material it should have maximum material at the outermost fibers. Okay, at the outermost part, because the bending stress will be maximum at the outermost part only. Okay, right? But here you can see that this section is not what you can say that this section is basically it is having maximum area towards this neutral axis. Basically, you can say that. Okay, so when the yielding will start from this fiber and this fiber, it will yield towards neutral axis, plastic neutral axis. Okay, and when we are moving internally, you can see that the area is increasing. Okay, area is increasing, right? Area is increasing. So basically the here area is basically increasing, so that's why we are getting this shape factor equals to 1.698. okay, in comparison to this hollow section, if we are saying that first compression yield will take place at this fiber, and here also the tension yield will be at this fiber. Okay, so when the yielding will start, again this portion will yield, okay, but the cross section is very less. As we are moving inward, the cross section is very less, right? So that's why its shape factor is less. Okay, there is not much difference. There is only 20% difference between the MP value and My value. Okay, in the same way, when we are considering this what you can say the diamond cross section, first this portion will yield. Okay, again when you are moving inside, you can see that the cross section area is also basically increasing. More and more cross section area is increasing towards this neutral axis. Okay, but for calculating My, there at the outer fiber there is less area. Okay, but as we are moving inside, the area is increasing. Okay, so sigma y into area, this value will also increase, which when we are moving inside, right? So that's why this shape factor is coming out to be 2. Okay, as we are moving inside, the area is also increasing, right? That's why for this cross section, the what you can say that the shape factor comes out to be maximum. So guys, I hope I made my point clear. If you have any doubt, you can write in the comment section. Okay, so this is the basic idea of the shape factor. What is the importance of the shape factor, right? So thank you very much.